All right, so this begins our lesson on the introduction to Newton's second law. So we've already learned about how mass and net force affect acceleration. We've talked about how we can use proportional reasoning to make predictions on what would happen to acceleration when we change net force and mass. And now we're going to put all of that understanding together into making one nice, neat equation that we can use to solve for net force or mass or acceleration in any circumstance where an object is accelerating. So our goal by the end of today's lesson is to be able to calculate acceleration of any object that's experiencing a net force. And we're going to do this by using the Newton's second law equation. So before we get started, let's talk about the difference between Newton's first law and Newton's second law. So Newton's first law and Newton's second law are kind of just talking about two different circumstances. If an object is experiencing forces that are balanced, that means that all of the forces that it's experiencing are being balanced out by one another. So in other words, there's no net force. In an instance where an object is experiencing no net force, it is not going to accelerate. In other words, it's going to stay at rest or it's going to stay in motion at a constant velocity. So Newton's first law pretty much states that objects continue to do what they're already doing. Or in other words, this is a restatement of the property inertia. That objects like to keep on doing what they're already doing, and they're not going to change unless they're experiencing a net force that causes them to change. Which leads us to our other circumstance. What if an object is experiencing unbalanced forces? Maybe not all of them are unbalanced, but maybe one of them is unbalanced, or two of them are unbalanced. In this circumstance, when forces are unbalanced, that means an object is experiencing a net force. And in this circumstance, it's going to accelerate, which means one of two things, or even three things. If objects are accelerating, that means they're either speeding up, slowing down, or the third circumstance, they're changing direction. And changing direction might seem like it's not really a change in velocity, but truly it is. If we think about changes in direction as in changes in motion, it makes sense. Acceleration means that an object is changing what it was originally doing. So a change in direction must fall under that acceleration category, because to move at a constant velocity north and then to be moving at a constant velocity west, there must have been some change to cause that to happen. And during that time where we were changing direction, we were accelerating, or in other words, experiencing a net force that caused us to change direction. So that being said, net force is always produced by unbalanced forces. So if we were using a force diagram that looks like this example pictured here, we could find net force by figuring out what forces are unbalanced and taking the difference between them. So I see that my upwards force and my downwards force are both 20 newtons, which means they're congruent. Therefore, these forces are balancing each other out. However, my horizontal forces are not congruent. I've got a 10 newton force, leftwards, and a 40 newton force rightwards. These are not going to balance out. 10 newtons will balance out 10 newtons pointing to the right, leaving a net force, or an unbalanced part, of 30 newtons. So in this circumstance, this object is experiencing a net force of 30 newtons. Now, since forces are vectors, direction matters. So what I've drawn on this picture is that my net force, my unbalanced part, is pointing to the right. Therefore, the direction on my net force is rightwards. Now, let's talk about those relationships, those proportional relationships we discussed yesterday. Yesterday, we discussed that acceleration is affected by the mass of the object, and it's also affected by the net force that that object is experiencing. In our lab, we saw that when we increase net force by a factor, in other words, if we doubled net force, acceleration increased by the same factor and doubled as well. In other words, acceleration and net force are directly proportional. Now, when mass was altered, if we took our object and we doubled the mass, we saw that the acceleration was affected, but not in the same way. Our acceleration decreased by that factor. So if I doubled the mass of my object, my acceleration was cut in half, or in other words, it was divided by 2. So my acceleration and mass are inversely proportional. So if I were to put these two relationships together to make an equation, what I would see is that acceleration is proportional to the net force divided by the mass. And if there was a constant that was keeping these two sides from being equivalent, like a K constant, I could leave my statement as that. But through extensive testing, what we've come to find is that there is no constant other than 1. So this proportionality statement is actually an equation. This is what Newton's second law's equation is. Acceleration is equal to the net force the object's experiencing divided by the object's mass. Now, this is one way to write the equation. One of the more popular ways to write the equation is reorganizing the terms so that there are no fractions, and writing it as net force equals mass times acceleration. Either equation is acceptable to use, and they both say the same thing. So that being said, let's get some practice using these equations. So let's do this first example together. Let's say we've got this object's force diagram. We're going to determine the net force it's experiencing, and then we're going to use that net force to calculate the acceleration that the object would experience. So let's look at the diagram and start with figuring out net force. So I can see that my vertical forces are equal and balanced. My horizontal forces are not, though. I'm going to have an unbalanced force or leftovers in the right direction. So my net force is going to be the difference between 36 and 24. And when I take that difference, I get 12 newtons for my net force. And the direction on this is to the right. Now, if I want to solve for acceleration, the equation that I'm going to use is Newton's second law. Acceleration equals net force divided by mass. Now, the problem is that we've got net force, which is 12 newtons. What we don't have is mass. That wasn't given to us point blank in the diagram. What we have to do is we have to calculate the mass. And I'm going to show you how we do that. It's using an equation that we learned last semester. If we wanted to figure out the force of gravity an object was experiencing, and I'll make this note in the corner, all we had to do is take the mass that it has in kilograms and multiply it by 9.8 newtons per kilogram. And that's how we would find the force of gravity. So it follows then that mass can also be calculated from that equation. All I have to do is take my force of gravity and divide by 9.8 newtons per kilogram. So we can calculate the mass of any object given its force of gravity or its weight. All we have to do is take its weight in kilograms, or its weight in newtons, and divide by 9.8. And that will get us our mass in kilograms. So let me plug this in for our specific situation. So our force of gravity is 30 newtons. If I were to divide that by 9.8 newtons per kilogram, we get something around 3. But let's plug it in a calculator just to be sure. So 30 divided by 9.8 gets me an exact mass of 3.06 kilograms. So this will be the value that I plug in for mass into my Newton's second law equation. So I'm going to show my work down here. Acceleration for this object is going to be equal to 12 newtons divided by 3.06 kilograms. And when I divide that, I know I'm going to get something around 4. But let's plug it in the calculator to get the exact value. Yep, I get 3.92, which is really close to 4. And the units on acceleration are meters per second, or meters per second squared. Now, acceleration is also a vector. Just like how velocity has direction, acceleration does too. If my net force is pointing to the right, then that means my acceleration is also going to be in the right direction. So my full answer, my complete answer for my acceleration would be that this object is going to accelerate 3.92 meters per second to the right. So let's do another example together. Actually, let's have you try this one, as this is our last example, so this will be your last opportunity to try it and see if you did it right and get feedback. So pause the video and attempt this one. When you're ready to check your answer, you can unpause. All right, I'm going to assume that you're unpaused and you're ready to check your answer, so I'm going to get started. First things first, I need to determine my net force and my acceleration. So in order to find acceleration, I'm going to use Newton's second law, which means I have to have a net force to plug into the equation and a mass to plug into the equation. So my net force is going to be the difference between my unbalanced forces. So vertically, I'm balanced. Horizontally, I'm not. 25 minus 15 is going to leave me with an unbalanced force of 10 newtons to the right. Now I need to find my mass. I'm going to find my mass by dividing my weight by 9.8 newtons per kilogram. So the weight of this object is its force of gravity, which is 25 newtons. When I divide 25 newtons by 9.8 newtons per kilogram, what do we get? 2.55 kilograms. Very nice. So now I can plug these values into my equation and solve for acceleration. So my net force is 10 newtons. My mass is 2.55 kilograms. When I divide these two values, let's see what we get. 10 divided by 2.55 gets me 3.92. Wait, that seems like wildly the same. Wow, same exact answer as before. That's crazy. So 3.92 meters per second. I was just noticing it's the same exact acceleration as the previous one. That's wild. So since my net force is in the right direction, that means my acceleration is also going to be in the right direction as well. So my final answer for acceleration would be 3.922 meters per second to the right. Now, one important thing to remember is that the direction of acceleration is not the same thing as your direction of movement. I'm going to clarify what I mean by that, because that could be kind of confusing. But direction of acceleration is not the same thing as the direction of the movement, the direction that you're moving in, I should say. So in other words, if I'm accelerating to the right, it doesn't necessarily mean that I'm moving to the right. If I'm accelerating to the left, it doesn't necessarily mean that I'm moving to the left. So I can experience a net force that's pushing me to the left and still be moving to the right. In fact, you've probably experienced this if you've ever walked like on a windy day. You've experienced a force that's pushing you maybe backwards, yet you're still walking forwards. So you can move in opposition of your acceleration or your net force. And in those instances, you might remember you slow down when you move in the opposite direction of your acceleration. So let's say that we had an example, and this actually looks like the same force diagram as what we just did, and we were asked to describe 2 ways that that object could be moving. Well, since this is the same example, I'm not going to spend time working out the problem. What I'm going to do is I'm going to think of this very qualitatively. If I can figure out what direction my acceleration is, that's going to help me get started with describing how this could be moving. So what I mean by that is this object right here appears to be balanced vertically, but its forces aren't balanced horizontally. There's a net force pointing to the right, which means its acceleration is also to the right. So there are 2 situations that could be happening, or in other words, 2 ways that this object could be moving. The first way is that its velocity is in the same direction as its acceleration. In other words, the first circumstance is that it is moving in the direction that it's accelerating. And if that's the case, the object would be speeding up to the right. So just based off of my force diagram, I could say that the object could be speeding up rightwards. However, there could be another situation. If my object's actually moving to the left and its velocity is leftwards and its acceleration is rightwards, that would be a different situation. It would no longer be speeding up to the left, it would be slowing down since acceleration is opposing its motion. So my second situation would be that the object could be slowing down to the left. So when we're given an acceleration, we can't assume what direction the object's going in. All that we can say is what the object could be doing, and it's always going to be one of these 2 circumstances. The object is either speeding up or it's slowing down. And we'll talk about situations where maybe it's changing direction in our future units. But for now, attempt to do this last example as a try. Pause the video and unpause when you're ready to check your answer. All right, I'm going to assume if you're listening to this, that means you're ready to check your answer. So we've got a different force diagram, which means we've got a different situation. Our net force, our unbalanced force, is pointing to the left, which means our acceleration is also to the left. So there are one of 2 situations that we could have. The object could be moving to the left and accelerating to the left, which means it could be speeding up leftwards. The opposite situation could also be happening. It could be moving to the right and accelerating to the left, which would mean it's slowing down to the right. So one of these 2 situations is happening, and we'd only be able to know which it is if we were given the direction it was moving in. So that being said, we've got all of the skills now to be able to solve problems using this second law equation. So you are ready to move on and start putting this learning objective into practice.